So we're being recorded. Okay, so we know that we can find the length of a line segment using the distance formula. Okay, and that is a line segment is a type of arc. It's just a straight arc. But what if we wanted to find the length of a more complicated arc, like you see here in figure 1? Okay, what if you wanted to find a more complicated arc? Well, the length of a more complicated arc. How can we do that? I mean, you can imagine there are important applications to finding lengths of arcs, like the length of a road, for instance. A road isn't straight all the time, right? There are curves and so forth. So what we want to think about is, first of all, our curve C, this arc, we need to have some model that will generate the curve. And we can get that model using parametric equations. How many of you remember parametric equations from pre-calculus? It's something everybody should have seen before. How many of you are parametric equations new to any of you, or have you? Normally we cover it, it's covered in pre-calculus. Okay, Rodrigo remembers. Tina is a little bit new. Mohammed, a little bit new. Okay, Snega. All right. Well, we'll talk about that. All right. So I think people kind of recall it, but a little review wouldn't hurt. Okay. Thank you, everybody, for that input. I always like to get input. So how would we but let's not. I mean, let's not worry about. Well, let me see here. All right, hang on. Let me share the whiteboard for a moment and just discuss an example. I'll give you an example of two parametric equations that will help us draw something. Okay, so we're going to have an x-axis and a y-axis. And let's say, well, let me see here. Let me do some labeling here. X and Y. And let's say that we had parametric equations given by X equals, so this is just an example of parametric equations. Let's say that X equals the cosine of t and Y equals the sine of t. So we have these parametric equations, X equals cosine of t and Y equals the sine of t. And what it's going to do is, for every value of t, you're going to generate coordinates. For every value of t, you're going to generate some coordinates. Okay, so like you could make a table. You can make a table here. And we could pick values of t, and then we could find coordinates. Okay. All right, and I'll just fill in on my picture here some values. This is a very simple example. All right, well, let's pick a value of t. Let's pick a value of t that would be interesting. And by the way, maybe what we'll do here, is we'll restrict t. We'll also say that we want t to be less than or equal to 0, or I should say greater than or equal to 0, and less than or equal to 3 pi over 2. Okay. So let's think of what's a good starting value if we want to graph this curve using the parametric equations. What would a good starting value be, you think? T is from 0. T equals 0. Colomb, I like that. Okay. So if t equals 0, what's the cosine of t? So we're finding the cosine of 0. Good, Snega. And we want the sine of 0. So the cosine of 0 is 1. And the sine of 0 is 0. Good. And so our parametric curve starts right here. That's the starting spot, 1, 0. Okay. Let's pick another value. Let's say t equals pi over 4. Okay, we would have the cosine of pi over 4 and the sine of pi over 4. What's the cosine of 45 degrees? Root 2 over 2. Good, Colomb. And the sine of 45 degrees? Also root 2 over 2. Now, root 2 over 2 is, let me see here, about 0.7. So this coordinate here is 0.7, 0.7. So that's going to be roughly here. Okay. So pretend you can think of this as like maybe there's a fly, okay, an insect, and the insect's flying on a path, and the path is given by x equals cosine of t. And I mean, let's assume it's I mean, we know insects fly in three-dimensional space, but let's just think 2 dimensions. Okay, x is cosine of t, y equals sine of t. So at time equals 0, the insect starts at coordinate 1, 0. and then at time equals pi over 4, the insect is at coordinate root 2 over 2, root 2 over 2. Okay, now I can tell you that this insect is going to pass through the point 0, 1. And at what time does the insect pass through the point 0, 1? So essentially I'm doing something. Well, you're going to see, Tina, and Colombe's right, pi over 2. So if you have the coordinate 0, 1, okay, so I'm just kind of separating things here a little bit. That would be when t equals pi over 2. Because the cosine of pi over 2 of 90 degrees is 0, and the sine of 90 degrees is 1. Okay. What about at negative 1, 0? That's right, Tina. At negative 1, 0, the time would be pi. And again, all you need to do is evaluate the cosine and sine of pi, and you'll get negative 1, 0. Okay, now t is between 0 and 3 pi over 2. So at 3 pi over 2, that's where the insect stops. Maybe it just stops after 3. Let's see, 3 times pi divided by 2, that's 4.7 seconds. What coordinate would it be at? Good. That's right. 0, negative 1. I'm in class. Good to see you. I'll get the garbage later. Okay. All right. So let me just finish this off here. Let me see here. There's a little error here. This should be t equals pi over 4. And this is t equals pi over 2. And this is when t equals pi. And this, of course, is when t equals 3 pi over 2. Okay. So now, let's trace out the path that this insect makes. And let's put an arrow on the path to show the direction that the insect is going. This is an example of graphing a curve based on 2 parametric equations. And what we're going to talk about in this class is, well, of course, we might wonder what's the length of that path? What's the length of that arc? Does anybody know offhand the length of this arc? It's not a full circle, but the insect is traveling in a circle with radius 1. Okay. What would the length be? What would L be for this? Let's see. 3 pi over 4. Well, you're on the right track, Cologne. You're on the right track. Actually, hold on. You got to be careful here. It would be 3 pi over 2. Tina's right. Tina's right. Because, good. Okay. Cologne used the area formula. So the length of the circumference of the circle is 2 pi r. But this has radius 1. This circle, but it isn't the full circle. It's just 3/4 of the circle. So you take 3/4 and multiply it by 2 pi. That gets you 6 pi over 4, or 3 pi over 2 as your arc length. Is this example helpful to those of you to refresh you on parametric equations? Are we all right? Very good, very good. And you know, your calculator has a mode on it. If you go to mode, there's a thing for parametric. Okay, if you look on the fourth line where it has function, parametric, PAR, you select PAR. Oh, you're welcome, Esther. You select PAR for parametric. So if any of you need to review how to graph on your TI-83, 84 calculator parametric equations, you know, there will be a YouTube video on it. Okay, but at any rate, now this was an example of an arc where we could find the length because we knew we've studied lengths of circles, circumferences of circles. But we want a more general ability to find the length of different arcs because not all arcs are going to be a circle. So on that note, let me go ahead and get back to the textbook here, and I'll show you this formula, how they derive it. Are we good so far? Are there any questions? Okay, all right, great. Well, then let's get back to the book here. Okay, so the idea here is if we have some arc given here in figure 3, we could approximate the length of that arc by inscribing some line segments. They've inscribed some line segments to approximate the length of the arc. Like they basically take the arc and they break it up into pieces and draw a line segment on each piece. Now the line segment approximates the arc. If we added up the lengths of all those line segments, we would get an approximation of the arc length. And if we took smaller and smaller line segments, the approximation would get better and better. If we took more line segments, and you know, then the line segments would if we added up the line segments, it would very well approximate the length of the arc. You can see it here in figure 4, here from point P sub I1 to point P sub I. For that arc, you know, it's the same in the 4 little pictures here. The first arc, they just drew 1 line segment. The second arc in figure 4, they drew 2 line segments. If you add up the lengths of the 2 line segments, you're going to get a better approximation than what you have in the first picture with 1 line segment. And then the third picture, they use 3 line segments, and then the fourth picture, they have 4 line segments. And if you add up the lengths of the, if you add up the 4 line segments, the length of each line segment in that fourth picture there in figure 4, you're going to get a pretty good approximation. Okay, but again, we want to find the exact length of the arc. So to find the exact length of the arc, we have to come up with a formula. For computational purposes, we need a more convenient, this is good, we need a more convenient expression for length. And so what they do is they say, well, look, if we let delta x I be the difference of 2 x coordinates and delta y be the difference of 2 y coordinates, then the length of the ith line segment would be the square root of delta xi squared plus delta yi squared. Now let me show you why that is. All right, hang on. Let me bring up the whiteboard again. I like to usually draw my arcs in red. So okay, there's an arc. And I'm going to pick two points on the arc. And I'm going to draw a line segment. So from the first point to the second point, I can approximate that arc length with the line segment, but I have to find the length of the line segment. So what we can do is we can, hold on. We can construct a right triangle here. And we'll call the one leg, the length of that leg, delta x. And if we're going, for incidentally, from some point p sub I minus 1 to some point to the next point, p sub I, okay, then we can call the length of that bottom leg delta xi, and the length of the other leg, we'll call it delta y sub I. Okay, and so, well, by the Pythagorean theorem, I mean, what we're interested in is in the length of this blue hypotenuse here, that line segment. We know by the Pythagorean theorem that that length would just be delta xi squared plus delta yi squared, but the square root. That's going to be the length of that line segment. And that's what they're calling, incidentally. They're calling that, they're representing that by, they're using absolute value signs, but it's sometimes also, they're calling that the length, well, it is the length of the line segment connecting p I sub 1 to the next point p sub I. And they're denoting that length with the absolute value of Well, they're denoting the length this way. This means length. That's length. Okay, and so are there any questions on that? Of course, I want to get back to the proof, but keep in mind that you move. I'll say something else here while I'm at it. You move from the I minus first point to the ith point over a time period of delta t. Okay, because remember, you have parametric equations, right? You have parametric equations. Okay, x of t, parametric equations given by x of t and y of t. And as t changes, and I'm trying to get this as good as I can get it, as t changes, as time changes, that causes you to move along that arc. That causes you to move along the arc. But you move from one point to another point over an elapsed time, but called delta t. Delta t would just be, it would be the difference in two times. Okay. All right. So let me be a little bit careful here. We can actually here, there's nothing wrong with what I wrote here, but I can be even more specific here. This is going to be helpful when we get back to the proof. Okay, so again, you know, you have these coordinates x and y, but x you can denote by some function of t, the x coordinate, and the y coordinate can be denoted by some function g of t. So the x of t and the g of t are, you know, there's all kinds of different notations, but the f of t and the g of t are your parametric equations. So like for the little example we did on the whiteboard, the cosine of t was f of t and the sine of t was g of t. Okay, so they're going to note here. They're going to have a little note that, you know, x equals, as I said, the x coordinate is given by some function of t. And so dx dt will be the same as f prime of t. Okay. But that means, and there's a reason I'm doing this, that means that your f prime of t can be approximated by delta x over delta t. You learned in calculus 1, right, that the slope of a secant line when your delta t is very small, the slope of a secant line, and that's what this is, delta x over delta t, that'll approximate the derivative. Okay. And similarly, y equals g of t. That means dy dt is equal to g prime of t. And again, I'm doing this note part. Well, I'm doing all of this so that when you see the proof, you appreciate the proof. So dy dt is equal to g prime of t. Well, then that means that dy dt can be approximated by delta y over delta t, and it'll be a very good approximation if delta t is very small. So g prime of t can be approximated by delta y over delta t. And actually, we can say, you know, delta xi over delta t on the left here, and delta yi over delta t on the right. So f prime of t can be approximated by delta x sub I over delta t, and you know what delta xi means. And g prime of t can be approximated by delta y sub I over delta t, and you know what delta y sub I means. Okay, so are we good with these little equations here? This arc length formula is a fascinating formula, and I want you to appreciate it. So, but now I'll get, if we're good, I'll get back to the book then and finish up the proof. But are there, and of course this is in the recording, but are there any questions so far? All right. All right. Thank you, Tina. All right. Well, very good. Well, then let's go back to the and this is, of course, all this is on the it's on the recording. Okay. So one moment. So now the delta x in here, the delta x and the delta x sub I and delta y sub I, we can replace that with the delta xi would be f prime of ti times delta t, and y sub I would be g prime of ti times delta t. So one thing I guess I forgot, I didn't put the sub I on the t. So like when I wrote it out, I wrote f prime of t, like if you go back to the recording, I mean back to what I did on Blackboard, and you probably have in your notes, I said the prime of t was approximately delta x over delta t, but it's really f prime of t sub I, okay? F prime of t sub I equals delta xi over delta t, and also g prime of t sub I equals delta y sub I over delta t. But you get the general idea. And what we're going to do is we're going to, in this length formula here, for the length of that line segment, we're going to replace delta x and delta y with f prime of ti delta t and g prime of t delta t. And when we do that, we can actually then factor out delta t squared from both of these expressions, okay, from both of these expressions. And when we do that, delta t squared becomes delta t. And so now the length of your arc is going to be, it's going to be the sum where I goes from 1 to n of the square root of f prime of ti squared plus g prime of ti squared delta t. Okay. But of course, if you let n go to infinity, the sum will become the integral. And so now you have this integral formula. Okay. And I thought that, let me see, I don't know why this isn't showing. Hold on. It's one moment. Hold on. Okay, so you all can see it now. All right, let me go back. Okay, so like I said, we in this formula now, in this formula for the length between 2 points, we replace the delta x and the delta y by f prime of t delta t, g prime of t delta t. And when we do that, we can then through math, you know, in here, what they do is they factor out they factor out a delta t squared from both terms, and when they do that, the square root of delta t squared becomes delta t, and so this gets them the approximation formula for the length of the arc, okay, which is right here in blue. And then as you as you take more, if delta t is a certain subinterval, right? A subinterval delta t. If you shrink delta t, make it smaller and smaller, you're going to get a better approximation. And in the end, you're going to get the Riemann sum becoming the integral. And so now you have the formula. You have the formula here for the length of the arc. And it's a general formula. So if you know your parametric equations, you can get the length of the arc. All right, are there any questions on that before we get to our examples? Okay, well, let's go ahead and get to our examples then. Okay, take a moment to copy this example down. Okay, so here we want to find the length of the arc described by these two parametric equations. And the arc lies between the points. The arc lies between the points 1, 1 and 4, 8. Okay, so at 1, 1, what's the value of t when at 1, 1? What's t going to equal? That's right, t equals 1, because, so, you know, the points are made up. The points are made up so that, I mean, the points have to be on the arc. So 1 squared is 1, x equals 1 squared, y equals 1 cubed when t equals 1. That's the one, that gives you the coordinate 1, 1. So the starting time is t equals 1. Okay. What's the ending time going to be? We end up at 4, 8. What would t have to equal there? T would have to be 2. Good, good. Good, Tina. Good, Rodrigo. Because 2 squared is 4 and 2 cubed is 8. Okay, so the formula for the arc length is that we're integrating with respect to t. Okay, if we're integrating with respect to t, because that's how we derived our arc length formula, and it makes sense because we're using parametric equations. With parametric equations, we can describe an arc very well. So all we have to do now is work on the formula. Okay, so what I've done here is I've drawn a graph of my arc. Okay, I've drawn a graph of the arc. Here it is. Starts at 1, 1 and ends at 4, 8. Okay, so all you need to do is put your calculator in parametric mode and set the window. So the window that I used was, so again, when you put your calculator in parametric mode, you know, you go to mode and you go down the fourth line where it says function FUNC and you switch over to PAR for parametric. That's how you put it in parametric mode. And when your calculator's in parametric mode, when you go to window, there's going to be a T min, a T max, and a T step, because you got to tell the calculator what your starting time is and ending time is. Well, the starting time was t equals 1, and the ending time was t equals 2. And the time, and you're skipping by t step of 0.1. And then for your x and y windows, I'm going to let x go from 0 to 10. X min is 0, x max is 10, and the x scale is 1. And then the y min will be 0, y max will be 10, and y scale will be 1. And again, if you need to review how to graph parametric equations on your calculator, all you need to do is you can just go to Google and there'll be a ton of YouTube videos on that. Okay. All right. So we've drawn this arc, and you know, I tend to like to draw the arc because it gives me an idea of what a reasonable answer is. Okay. So certainly, let me see here. Well, the length of this arc, I mean, if you had to approximate it, what might be a decent approximation for the length of this arc? If you had to just sort of take a guess, would the length be 100? Would that make sense? No, of course it won't be 100. Of course not. What might be a reasonable guess here? Maybe 3. Okay, Tina's thinking 3. Mohammed's thinking, he's thinking 5. Okay. Let me just see here. One moment. I mean, I have the true value, and what I'm doing is I'm trying to see who's closer. Is it closer to 3 or is it closer to 5? It's a little closer to 5. Okay, and it's more than 5. But let's find the exact length. So of course, x equals t squared. So the derivative of t squared dx dt is equal to 2t. Y equals t cubed. The derivative of y with respect to t is 3t squared. Okay, we're going to square each of those. So in the integral, you're going to get the integral from 1 to 2 of the square root of 4t squared plus 9t to the 4th. Are there any questions up to this step here? All right, well, so we need to get the exact value. We need to get the exact value of this arc. So in WebAssign, in the homework, when they tell you that find the exact length of the arc, it means you can algebraically find it. You can integrate, and you can get an antiderivative. Okay, so WebAssign will not accept an approximation when an exact answer can be found. Okay, so keep that in mind. Again, when you take your next exam, there were a few students that thought, like when an exact answer was possible, they would put in an approximation, but that's not good enough. That's not correct, right? There's a big difference between an approximation and integrating to get the exact length. So, okay, well, I have here, I'm going to factor here from the 4t squared plus 9t to the 4th, I'm going to factor t squared. Why would I want to do that? Why did I factor t squared out? I mean, I'm right here at this step. Okay, how can we simplify? How can we simplify, Tina? How can we simplify? What happens to that t squared? That's right, it comes out of the root, because, very good, because remember, the square root of a times b is equal to the square root of a times the square root of b. So t squared comes out as a t. All right, I mean, what you're doing here, I mean, I'll maybe put in a little step here. The square root of t squared, because this seems to be something that some students have a hard time doing. But that the square root of t squared times 4 plus 9t squared is just the square root of t squared times the square root of 4 plus 9t squared. And the square root of t squared will come out then as this t here. Now, technically, the square root of t squared is the absolute value of t. But since t is between 1 and 2, the absolute value of t is just t. Are there any questions up to this stage right here? Up to that step? All right, well, can we integrate that? Can we integrate this? So the answer, of course, is yes. How would we integrate this? Substitution is right. What substitution would we use? What are we going to let u equal to? Good, 4 plus 9t squared. It's absolutely right. And so when we do that, by letting u equal 4 plus 9t squared, we'll get that t dt equals 1/18 du. And so now our integral with respect to u, our length, our arc length, is going to be the integral from 13 to 40 of the square root of u times 1/18 du. And of course, the 40, that just comes by taking 4 plus 9 times 2 squared. Okay. Hi, I'm in class. Hi. Hi. And then 13 is 4 plus 9 times 1 squared. Okay, are there any questions so far? Okay, well then let's move to the next page then. Oh, let's see, Notnell, thank you, Mohammed. Notnell says that you get the square root of u by using u. Yes, yes, because u was equal to 4 plus 9t squared. So then I get the square root of u here. So what I'm doing is I have an integral here. You know, here's my length integral. I'm doing a substitution so that I can get the antiderivative. I agree, Justice. It's not so bad. It's not so bad. Okay, well then let's move on. So now here's our arc length. The integral from 13 to 40 of the square root of u 1/18 du. And then this is just an easy integral. This is like no problem. So the antiderivative, I factor the 18th in front. And the antiderivative of u to the half is 2/3 times u to the 3/2. And 40 and 13 are the values that we're using. And so I just put them in. And WebAssign would take this answer. The length is 1/27 times 40 to the 3/2 minus 13 to the 3/2. But you can also write the answer. It can be shown that that answer can be also written as 1/27 times 80 root 10 minus 13 root 3. And I have the work over here. I guess, let me see here. Let me just write 13 to the 3/2 is 13. The half, my exponent's pretty big. One moment. Oh God, hold on. I clicked on the wrong thing. Hold on. One moment. Let me bring it back. One moment. What I'm trying to do here, I guess the scan got cut off. Not now. I'll get to your question, but hold on. (13 to the 3/2 power) is 13 to the 1/2 power raised to the third. We can write it that way, which is √13 times √13 times √13. And that's how you get 13 times √3. I'm trying to show you how I got the 13√3. And then regarding the 80√10, that's shown over here. Now, let me see. Notnell had a question. One moment. No. It should be what, u minus 4. No. This integral here. This integral here is for the length. That integral is correct based on the substitution. Did you sort it out, Notnell, where? Yes, Serfio. WebAssign would take this answer, unless it said, it needs it in simplified radical form. I like this answer, the second answer, better. But WebAssign would take the 1/27 times 40 to the 3/2 minus 13 to the 3/2. It would take that. The 1/27th, the way we get the 1/27th is on this step here. Notnell's wondering where the 1/27th comes from. So in the work here, I'm taking an 18th and I'm going to multiply it by 2/3. And that's how we get the 1/27th. 18th times 2/3 is 1/27th. All right, great. Are there any other questions before we move on to our next example? So again, sections, I think this section, this section just takes a little time. Okay, well then let's move on to the next example. All right, take a moment to copy this down. Okay, so in this problem, we want to find the length of the arc of the curve described by the parametric equations x equals 3 times e to the t cosine of t and y equals 3 e to the t times the sine of t. And we're letting t be between 0 and pi. So again, we're going to use the arc length formula. We know we have to take the derivative of x with respect to t and the derivative of y with respect to t. All right, so if we're good, I'll move to the next page. All right. So what I've done here is, first of all, I drew a graph. This is what this arc looks like. Starting at t equals 0 and ending at t equals pi, this is what the arc's going to look like. So to use the formula, we have to find the derivative of x with respect to t and the derivative of y with respect to t. And of course, we're going to use the product rule in each. Let me give you a moment to copy that down. All right. And now, here's our arc length formula. Okay. And in my book, it's on page 456. It's, but in the MindTap in the ebook, it could be, I don't know what page it is, but it's in section 6.4. So yes, this is what we have to do. We have to some reason, let me just see here. I need a dt at the end here. So I take three, so we apply the arc length formula, and I wanted to do kind of a hard one with you, okay? Because sometimes you have to, you have to just kind of, these problems involve simplifying your expressions so you can get your integral. There's usually a simplification of some kind that needs to be done. And of course, not all the problems can be done using you can't get the integral. To find the exact arc length, you need to be able to find the integral. You need to be able to get the antiderivative. There are some problems where you can't get the antiderivative. And so there you have to use your calculator to compute the definite integral. But WebAssign will let you know in the instructions about that. It'll say, if it says approximate your answer to the nearest hundredths place, something like that, that means go ahead and use your calculator to get the answer. I mean, you know, you have to write out the work until you get to the part that you got to put in your calculator, but you can use your calculator to get the answer. But if it says find the exact length in the WebAssign, you know, in the homework, then you can get the antiderivative. And what we have to do here is, like for instance, the dx dt is 3et cosine t minus 3et sine t, and we're squaring that. So of course, when you square it, it helps me to just, you know, write it out and then do FOIL. And when I do FOIL to multiply 3et cosine t minus 3et sine t by itself, I'll get 9e to the 2t cosine squared t minus 18e to the 2t sine cosine t plus 9e to the 2t sine squared t. Okay. So this is like your first term. The negative 18e to the 2t sine t cosine of t comes from adding your inner and outer terms, your outer and inner terms. And then the 9e 2t sine squared t comes, that's the last. That's from multiplying negative 3et sine t by itself. And then similarly, for the other term that gets squared, you'll do the same thing. You'll FOIL, and you'll get this here. You'll get 9e 2t sine squared t plus 18e 2t sine t cosine t plus 9e to the 2t cosine squared of t. That's what you'll get. dt, don't forget the dt. Okay. So hopefully, Justice, I'm hoping you're still feeling good. Justice said this isn't too bad. Uh-oh, Justice has now changed his mind. Well, hold on though, Justice. Hold on, Justice. Does some nice things happen here in this, you know, where we have the length here? Okay, where we have the length. When you look at the integrand, does some nice stuff happen? Does some canceling happen? You have 6 terms, 6 terms. Does something nice happen at all? Two terms cancel. Okay. All right. Very good, Rodrigo. Very good, Justice. So this term will cancel with this term. And so what that's going to leave you with then, I'll move to the next page if we're okay. Well, also, hold on. Other good things happen too. Other good things happen too. What about this 9e 2t cosine squared t? We can combine it with this at this last term, 9e 2t cosine squared t. That would give us 18e to the, they add up. That would give us 18e to the 2t cosine squared t. That's right, Tina. They add up. And also, this term here, 9e 2t sine squared t, will add with 9e 2t sine squared t here. Those terms add up. Okay, and so when you do that, you're going to get then that the length equals this. The integral from 0 to pi of the square root of 18e to the 2t cosine squared t plus 18 e to the 2t sine squared t. Justice, are you feeling a little better? Are you a little more optimistic? A little more optimistic now? Uh-oh, Justice says no. Okay. Well, I appreciate your honesty. Well, look, you know, we have here a common factor. Under the square root, we have an 18e to the 2t. So we can certainly factor that. And if we factor it, we're going to get 18e to the 2t times cosine squared of t plus sine squared of t, but that just equals 1. And incidentally, e to the 2t can be written as e to the t times e to the t, and the square root of that would be then e to the t. Well, Justice, it is a lot of terms being added up, and so you have to be careful not to lose track of the terms. That's the challenge, but you know, now we got a pretty nice integral. Pretty nice integral here, where we can find the arc length. And remember, in this problem, as well as the last, t is your parameter. Your parametric equations are both written, the x and the y are both written in terms of t. So t is what's called your parameter. And so you're going to get then the length is 3 times the square root of 2 times e to the pi minus 1. So it's actually a very nice thing to be able to get the exact. How many find this kind of fascinating? That they can find the length of these arcs. You know, you knew how to find the length of a circle, you know, which is the circumference of a circle, and the length of a line segment, but now you can find the length of a lot of different other kinds of curves. How many think that's kind of cool? Who thinks that's kind of cool? Uh-oh, we're not. Okay, Tina likes it better than the volumes, okay. How many found the volumes to be a little bit challenging? I think probably you did. The students tend to find them hard, but remember, you know, you're in calculus 2 now, so you know you're well, Michael, I agree here. You don't have to worry so much about drawing. I mean, it's helpful to draw a little picture, but it's not three-dimensional. You know, you're not having to think 3 dimensions. Now, when you take calculus 3, you'll learn about arc length in 3 dimensions, a curve going in 3-dimensional space when you take calculus 3. I'd hope, it'd be nice to teach it. I've taught it before. Maybe I'll see you again in calculus 3, but right now, let's worry about calculus 2. Are there any questions before we move to the next example? Okay, well then let's move on. Okay, now I called this review, but it isn't really review. It's an example. right. I'll give you a moment to copy that. Okay, so now in this problem, we want to find the length of the arc of the curve where y to the 3/2 power equals x from 0, 0 to 1, 1. So of course, this is the same as saying x equals y to the 3/2 power. Okay, now what is missing? Well, first of all, if we wanted to graph this on our calculator, right, I mean, this is equivalent to saying that y, well, let me phrase it the way I want to phrase it. If we were to get the y by itself, we could raise both sides of this equation by 2/3. Two-thirds power. Because y to the 3/2 raised to y to the 2/3, you multiply the exponents. That gives you y to the first power. So y to the first power, which is y, will equal x to the 2/3. Okay, and if we graph x to the 2/3 on our calculator, and I'm actually doing that right now as we speak, because I'm curious what this looks like. I assume, okay, so it's going to look, it looks something, I mean, we're restricting ourselves from the origin to 1, 1. So the curve's going to look something like this. Okay. And it goes in this direction. But there's something about this problem that makes it a little different from the last two that we did. There's something a little bit different about this problem. What makes the problem different? What's missing that you saw in the other problems? The t. That's right. The t is missing. But here's the thing. You can let any variable be your parameter. You don't have to let t be the parameter. I mean, I graphed this curve, I graph this curve, and we're looking at the curve, and it has a length. So we ought to be able to find the length. So here's how I like to handle this, okay? There's several ways you can handle it, okay? First method is, you could, instead of letting x be the parameter, you could let y be the parameter. And y would make sense. Y would make sense because x is a function of y. X is y to the 3/2 power, right? So what I do is I say, okay, the normal arc length formula, where t is the parameter, is the integral from a to b of the square root of dx dt squared plus dy dt squared dt. But that's when t is the parameter. But if I'm going to let y be the parameter, then wherever I have a t in the arc length formula, I'll replace it with a y. So the formula then becomes the integral, the formula I'm going to use with this first method, where y is the parameter. The arc length will be the integral from a to b of dx dy squared plus dy dy squared dy. But what is dy dy? That equals 1 squared. That's 1. So my length, using this approach, the arc length would be the integral from a to b of the square root of dx dy squared plus 1 dy. How many kind of like that, doing it that way? All right, it might seem a little strange, but the point is you can let, I mean, basically what you're saying is if you let y be the parameter, okay, if you let y be the parameter, then here are your parametric equations. X equals y to the 3/2. Maybe I'll be, well, yeah, let me do it even better here. Hold on. You can think of it like this. X as a function of y is equal to y to the 3/2. And then y as a function of y equals y. I don't know if that's helpful or not. Maybe it'd be more helpful this way. Hold on. One moment. Hold on, let me just, maybe it'd just be better to write it like this. X is y to the 3/2 power, and y equals y. Okay. All right, and so what we have to do then is we put in are derivatives. Dx dy is, hold on, I don't know why my thing's doing that. All right. Dx dy is 3/2 times y to the half power. And then this is your formula. And incidentally, let me just go back. I'm going to say, instead of for the example, right? This was our example. I mean, you have it written down, but for the recording, I wish it would kind of keep the writing that I do, but you know, it's fine. I'm finding expressions. For the length of the arc. Okay. So modify that example to say you're finding expressions for the length of the arc. Okay. Because what I do is, in this, I don't go all the way with it. I basically get to this step, and I don't do any more. Okay. You could get the answer on that. Second method, of course, would be to let t be the parameter, because you're used to letting t be the parameter. But what you have to do then is you have to let y equals t. So remember, you have x equals y to the 3/2. So in this case, y is your independent variable. So if you want to use the arc length formula as like the one where t is your parameter, you could just let y be t, and then the curve x equals y to the 3/2 becomes x equals t to the 3/2. Okay, and so then you can apply the formula directly, and you'll get the you'll get the same answer. Well, you'll get this expression. How many like the second method? How many like the second method? Okay, Michael likes the second method better for the arc length. How many like the first method? Okay, not Nell likes the first. Okay. People are different. You know, people are different. The one advantage of the second method is well, it just depends how. It just really depends on you. You know, it depends on you. So I mean, I know that I can graph this curve in regular function mode, or if I let y equals t, I can, and then x would be t to the 3/2. I could graph the same curve by putting my calculator in parametric mode. So either way. And another thing too, I'll note here. So the first method, you got an integral with respect to y. The second method, an integral with respect to t. But you'll note that both integrals will give the same answer. Okay, sometimes students think, oh, a different variable, I'm going to get a different answer. Not the integrand's the same for both of these integrals, and the limits are the same for both of these integrals. So you're going to get the same answer. All right, are there, well, what'll happen, Felicity, is, I mean, you have to again get your answer. I mean, we found the expressions for the arc length, but then, WebAssign's going to want then, what's the answer? What's the final answer? That's what WebAssign's going to want. How did we get the 1? We got the 1 because the arc went from 0, 0 to 1, 1. So one of the limits will have to be 0. One of the t-limits has to be 0, and the other t-limit has to be 1. Because you know what you're doing is you're saying, okay, let y equals t, and let x equals t to the 3/2. And so you're going from 0, 0 to 1, 1. And so starting value of t has to be 0. Because, putting t equals 0 in both of your parametric equations here will get you 0, 0. And then putting t equals 1 in both your parametric equations will get you 1, 1. So Felicity says, can we write the answer in terms of t? Well, see, you're not going to get an answer in terms of t, Felicity, because this is a definite integral. So what I did was, you see, I didn't want to go through, take time to get to the final answer, the exact arc length. But I'm just showing you how you can use 2 different ways to do the same problem. 2 different ways to do the same problem. I mean, the rest of this you could do. All right, Tyreek, are you good? Comfortable? Good. Felicity says, do we have to write the answer and why? I guess I'm not. Either way will work. But this is not the final answer. You understand? This is not the final answer. It's an expression for the arc length, and that's what we did. So remember, I altered the instructions. I said instead of find the length of the arc of the curve, I said find expressions for the length of the arc of the curve. And that's what we did. That's okay, no problem, Felicity, no problem. I corrected the thing in my notes too, so that, all right, great. Are there any other questions on this before we move on? Okay, I'll stop the recording.